my talk is about a theorem of Diron-Searle and how it implies, and I will explain later what it means, but it gives us things called vertical versus horizontal inequalities on Cardinal groups. So my talk will consist of 3 parts. First, I will discuss the classical differentiability theory on Euclidean spaces. Then I will discuss Diron-Searle's theorem on objects called Cardinal groups. And then I will discuss what it means what I mean by a vertical versus horizontal inequality on Cardinal groups, which tells us quantitative non-embeddability of Cardinal groups into LP spaces. So to begin with the first part, I will start off with a relatively simple note where this is stuff you learn in calculus. So if you say that u is a real valued function defined on Rn, and x is any point in Rn, and if you denote by t dxu, the Taylor polynomial of degree at most d of u at x, of course if it exists, we will denote it by that, then the basic theory you learn in calculus is the idea of continuity and differentiability. So continuity says that if you take a point y near x, then the difference of u of y and u of x approaches 0. So that's the denotation little o of 1 means that it goes to 0 as y goes to x. And if u is differentiable x, u of y minus, pardon me, the h should be t1 x of u. It's just I wrote a because it is an affine function, and you can approximate u by a linear function to get a smaller error, little o of y minus x, as y goes to x. And if you can differentiate u d times in the neighborhood of x, such that the differentials are continuous, then you can actually approximate u by its dth order Taylor polynomial with a much greater precision, namely little o of y minus x to the dth power as y goes to x. So the basic idea behind this continuity and differentiability is the idea that you can approximate a function by some polynomials. So the idea that, to recap, what this means is that what d times differentiability means is that you can approximate the function by polynomials of degree at most d at around that point at a very small scale. So the natural question you can ask is, well, usually in real life applications, you want to guarantee that the function can be approximated by that polynomial at larger scales. If you have it's the approximation at very small scales, like 10 to the minus 10, then it won't be very useful in many applications. So you want to know whether it can be approximated at larger scales, like 10 to the minus 1 or 1. And you want to know whether it can be approximated at many points as well. So one hint that goes in this direction is a theorem of Watermarker. So it tells us that a function can be differentiable almost everywhere, if you want to know what that means. So a function u from Rn to R is said to be Lipschitz continuous if there exists a constant L called its Lipschitz constant, such that u of x minus u of y can be bounded by L times the x minus y. So, and you can see that if a function u is continuously differentiable, then it has to satisfy the Lipschitz condition. And Rademacher showed an interesting converse. So it says that if you have a Lipschitz continuous function u from Rn to R, it has to be differentiable almost everywhere. So in other words, the weaker condition of Lipschitz continuity actually implies differentiability if we're willing to discard a set of measure zeros. For those who don't know what that means, it means that it's a set with measure zero just means volume zero, like a plane or a line in R3. So, and the contribution of the Dorn-Searle in question is the following theorem. So, it says that if U is a square integrable function in an L2, such that its gradient is also square integrable, then you can actually you actually have this somewhat remarkable inequality where this simple means that those expressions are equivalent of two constant factors. So the right-hand side, this might look complicated at first, but this means that if you integrate over x over all points and integrate over r, this expression, which expresses the deviation of u, the deviation of the function from being a linear function at all scales, then what happens is that this integral has to be equivalent to the one on the left-hand side, and in particular, it has to be finite. So you can see that because the integral over dr and dx are infinite, it tells you that what you have with the expression inside the integral in dy has to be small for for most points x and scales r. So that should be the end of part one. No. Oh, no, sorry. So the Dorn-Searle theorem actually extends to higher degrees where if it says that if U is a square integrable function such as dth order gradients are also in L2, then a similar theorem holds where the square integral of the dth gradient is actually equivalent to a similar expression you get by approximating U by dth degree by its dth degree Taylor polynomial. So it tells you that so roughly the philosophy is that if you approximate a function by its dth degree Taylor polynomial, you should be able to detect whether it's d times differentiable. So a couple of remarks is that Dorn-Searle actually proves in his paper a somewhat stronger statement. So d is in fact allowed to be any positive real number. In this case, on the right-hand side, d is replaced by the integer part of d. And on the left-hand side, you replace the nabla d by the dth order fractional Laplacian of u. And this actually works for LP norms instead of L2 norms if you replace the exponents suitably. And you can take different exponents when you're integrating in dy. And he proves that a converse holds, namely that the finiteness of the right-hand side, if you have a square integral function u, you don't know whether it's d times differentiable, but if you know that the right-hand side is finite, it tells you that u is d times differentiable almost everywhere, and the dth order derivatives are in L2. So that should be the end of my first part. And does anybody have any questions so far? Yes?
So the theorem at the top of this page right here says u is in L2, but near the bottom of the book it says that it works for LP where it would be strictly between 1 and 2.
Yes.
So in this case, would this also work, or has there been research done to see if this can work in L1, or is it just like greater than 1 also?
L1 is a very fickle case, and I am not aware if it is true in L1, but one obstruction against that is that L1 is not uniformly convex. So I don't have a good answer to that. Yeah. Certainly, in the case of the Cardinal groups that I will explain later, the L1 case will probably not be true because there are counterexamples in Cardinal groups. Any other questions so far? If not, I'll go on to the next part. So I will So my work is extending the Differential theorem to Cardinal groups. So what is a Cardinal group? So I'll give you a simple example, which is the Heisenberg group. So the Heisenberg group, the three-dimensional Heisenberg group is the matrix group of unipotent upper triangular 3×3 real matrices. So in notation, it's that 3×3 matrices that are upper triangular with ones on the diagonal. Because I said it's a group, we have to specify a group structure, and the group structure is given by matrix multiplication. And to put some spice to this, we can define a distance on it called the Karani distance, where it's defined to be that it defines the distance between g times x comma y comma z, and g to be x fourth plus y fourth plus z squared to the 1/4 power. So it's a left invariant norm in distance, in a sense that if you multiply both sides on the left by something, it will preserve the distance. And this has an interesting dilation structure where you have any positive real number lambda, and if you define a function map, a map delta sub lambda by multiplying by lambda on the on xy and by lambda squared on z, it actually becomes a group isomorphism from itself to itself, and it multiplies the distance by lambda. So a Cardinal group is an abstraction of this and of this space and the Euclidean space. So formally, I'll throw out a bunch of words, but a Cardinal group is a simply connected nilpotent Lie group. It just means that it's Rn with a Lie group structure such that its Lie algebra is graded. So it has S layers, V1 through Vs, such that V1 that bracket with V1 generates the next layer. And it's endowed with a left invariant sub-Riemannian distance associated to some distance on V1. And you can define the dilation delta sub lambda in a similar manner. They are again group automorphisms, and they scale the distance by lambda. And for those who didn't get what I said, it just means you can just take away the message that Cardinal groups are non-abelianizations of Rn, which still possess a dilation and a distance structure. So you can still perform analysis and geometry on them and compare them to what you get on Rn. So the theorem that I will present today is the following theorem. So, to make the notation make sense, we have to modify the notation a bit. So in this case, nabla denotes differentiation with respect to vectors in the first layer only, V1. And T at 1x denotes the first order Taylor polynomial with respect to variables in V1. And then the theorem that I am presenting today is that if you take the L2 norm of the gradient of a function u, then just as in the case of Rn, it happens to be that you get the same integral on the right-hand side. Namely, you can approximate a function u by its first order Taylor polynomial, and you can see that this expression is finite and is equivalent to the left-hand side. Of course, more precisely, what I've proven is that this is valid for all fractional orders and the LP cases, and you can get different exponents with respect to dy, and there is a converse statement as well. And I will remark that Fassler and Orponen have previously proven this in the case of the Heisenberg groups, while proving only one side of the inequality and up to only first order approximations. So that should be the end of part 2. Yes, I got it right this time. So are there any questions so far for this? So I'll go on to the last part, which describes the application, one application of this Differential theorem. So here's notation from metric geometry. So we say that a metric space M embeds bilopiously into some Banach space X if, with constant D, if there is a mapping F from M into X such that it satisfies the following double-sided Lipschitz condition. And the smallest such D is denoted C sub X of M, and is called the X distortion of M. And in the case of LP targets, we simply denote the distortion by C sub P of M. So the natural question to ask is, if we're given any metric space, does it embed into RD? Does it embed into LP? And if so, what is the best possible distortion? And to this, there is a well-established theory of the fact that you cannot embed Cardinal groups bilopiously into LP. So if we say that G is any non-abelian Cardinal group, Panzu has shown that if you have a Lipschitz map G into RD, then similar to the Watermarker differentiation theorem, this map is differentiable almost everywhere, and the differentiation is actually a Cardinal group homomorphism from G into RD. And based on this, SEMS has shown that there exists no biloxious embedding of G into RD, simply because if this were true, the Panzu argument would give a Cardinal group monomorphism from G into RD, which is impossible since G is non-abelian. And Jigger and Kleiner and Leonauer have independently shown that this actually shows that you cannot embed bilopiously G into any LP space where P is between 1 and infinity. And in the special case of L1 targets, which is special because it's not uniformly convex, Jigger and Kleiner have subsequently shown that you cannot embed H3 into L1. And Erickson, Bick, Gartland, Ladonna, and Lisa Naples, who is here, and Nicolas Igulo have shown that there exists no biloxious embedding of G into L1. I think Lisa will present the last sentence later today. So this tells us that these do not embed into LP. But the interesting but one thing you can ask is whether you can get quantitative versions of these statements. So how, even if it's like not embeddable into LP, suppose you take a large enough subset of the Cardinal group and ask whether it can embed, how much it distorts into LP. So to answer that question, let's look into the mechanism behind the Panzu-SEMS argument, which says that if you have a Lipschitz map from Cardinal group G into RD, it should collapse along the commutators because that's what its differentiation does. So if you measure the variations along the commutator directions, it should in principle be smaller than the variations you get along measuring the variations along the horizontal directions. So for an H3, it means that if you measure the variations of F along Z directions, it should be smaller than the variations along the XY directions. So to that end, I present to you this inequality, which tells you that if you have a non-abelian Cardinal group G and B equals 2, and if you have a map F such that is itself as regular on G, and if you come to computer direction G, then if you measure the variations of F along the constant direction and normalize it to what it should be, then along this particular integral, this particular integral tells you that because your R integral is infinite, the expression you get inside has to be smaller. So this tells you can use it to extract useful information about quantitative statements about how this mapping should collapse along the commutator. So this is proven from the Differential theorem on Cardinal groups, which was in section 2. And previously, for the case of the Heisenberg group, this was proven by Austin, Nauer, Teixeira, and Lefort and Nauer. And you can get the statement that if you have say gamma, a co-compact lattice in G, then the LP distortion of the ball radius n in G has to be at least the order of square root of log n. And this might be a strong restriction because not every Cardinal groups have lattices, but this inequality and this quantitative bound on the distortion is actually true in the more general setting of nilpotent Lie groups and violently generated groups of polynomial growth. So to hype up Lisa's talk later, I will talk. So one of the questions that I'm investigating is whether you can extend these inequalities for L1 targets. So if you have, so it asks whether you have the same inequality for L1 targets, and this was proven via much more difficult methods for the Heisenberg groups by Nauer and Young. And the question is, if we have the existence of any exponent q satisfying that inequality, we would be able to get a explicit bound on the lower bound on the distortion of balls of radius n. And that should be the end of my talk. Thank you. Yes.
So I asked before whether we could extend our source here to L1. And I should have asked earlier as well. Is there a reason why these theorems are only being applied to LP spaces with P being between 1 and 2? Is there something?
Well, it's a matter of the strength of our techniques rather than our objectives, because actually having L1 is the most desirable because it actually has because these have various applications to theoretical computer science, and in that case you want the L1 distortion. And in the case of Nauer and Young that is presented here, they had to resort to more refined statements on this shape of sets in the Heisenberg group to prove these inequalities. Thank you. The best explanation I can give is that in H3, if you take a vertical plane, it looks like R2. So the horizontal direction does not generate the vertical direction if you restrict to that plane. But in H5 or higher, if you take a codimension 1 subspace, it can generate the commutator direction. And so far, that's the reason I can see why this is happening here.
I'm going to talk today about Kernel groups and biloxious embeddings into L1. And this is the main theorem that I'm going to talk about. So every Kernel group that biloxious embeds into L1 is abelian. And just a very brief outline of the talk. I'm going to start with a review of Kernel groups. We just saw one in the previous talk, but I'll give another quick one. Then I'll review or define cuts and perimeter in the context of Kernel groups. Then I'll share a result by Jigger and Kleiner that shows the non-embeddability of Heisenberg Group into L1. And lastly, I'll talk about our result, which is an extension of Jigger and Kleiner via Ambrosio, Kleiner, and Ladone that eventually gives us this theorem. Okay, so when I say a Kernel group of step S, I mean a simply connected Lie group that has a Lie algebra, and our Lie algebra is stratified, so we can write the Lie algebra as a direct sum of Vi through Vs, where Vs is non-trivial. If we take the Lie bracket of V1 with Vi, we get Vi plus 1 as long as I is less than S. And if we take the Lie bracket of V1 with Vs, then we get the trivial element. So a couple of relevant facts about Kernel groups. First of all, this is the what the Lie bracket is for elements in the Lie algebra. Another thing to note is that step 1 Carnot groups are abelian, so step 1 Carnot groups can just be thought of as Rn. And so those will maybe not be as interesting for our particular talk. Another thing to note is that geodesics in the Carnot group are curves that move tangent to vectors in V1, and we equip our Carnot group G with the Carnot-Theodori distance. Okay. So I'm going to walk through the definition of Carnot group again with the Heisenberg group, which is a step 2 Carnot group, kind of our most simple example beyond Euclidean space for Carnot groups. So this is a slightly different definition for those of you who were, or different representation of the definition for those of you who were in the previous talk. I have 2 elements in R3, and the multiplication results in the thing on the right. And in particular, in the last component of the expression on the right, you can see the non-commutativity or non-abelianness of the group with that 1/2 x1 y2 minus y1 x2. Okay. Associated to the Heisenberg group, we have left invariant vector fields, and we see that with this x, y, and z, if we take the Lie bracket of x1 with y, of x with y, then we get back z. This is the stratification for the Heisenberg group. So our first level V1 is the span of x and y. Our second level V2 is the span of z. And below that are the properties in our definition of Carnot group. And then if we talk about horizontal curves or our geodesics for our group, these are going to be curves gamma going from 0, 1 into Heisenberg group, where the derivative is a linear combination of x and y, and then there's the Carnot-Theodori metric for us. Okay. So it was a conjecture by Lie and Noir that the Heisenberg group equipped with the Carnot-Theodori metric does not admit a biloxious embedding into L1. And in fact, this conjecture was proven true by Jigger and Kleiner. And so this led to the question, what results can we obtain from more general step S Carnot groups? So when we complicate our group, can we still prove the same result? Okay. And in order to answer this question, I'm going to need to define a few more things. So starting with cuts, we let cut G be the set of all G measurable subsets of G modulo the null set. So we can think about a cut as an equivalence class. Or if you don't like thinking about equivalence classes, for the most part, it's okay just to think about E as a subset of G. The equivalence classes are for some technicalities. We can also define the perimeter measure for a cut. And if you're familiar with the definition of perimeter measure from Euclidean space, then this definition should look the same or similar. In particular, in Euclidean space, that V1 is Rn here, and so that will really agree with the definition in step 1 Carnot groups. We say that E has locally finite perimeter if the perimeter measure assigned to any ball of radius r is finite. And we are mostly going to be working in the collection of cuts Fp log G. So this is the collection of locally finite, of cuts with locally finite perimeter. Okay. We're going to want to look at tangents for our cut. And so here's just some things that say basically we can take tangents as we do in Euclidean space. So we can define a dilation map on G and then a translation as well. We are able to pull back this map. So here's the pullback definition. And then we work with this map delta xr to define our tangents. And we say that a tangent is as follows. So we pick some sequence rj of scales that decrease to 0, and then a tangent of our cut E at x is just the L1 loc limit of the sequence delta rjx, and E as j goes to infinity. And so this is essentially similar to our definition of tangent in Euclidean space. Okay, so this is the only picture that I put in my slides, but in case anyone is not familiar with sets of locally finite perimeter, even in Euclidean space, you can think about just a nice set with C1 boundary as a simplified case. If you pick some point on the boundary of your set and you draw a ball around that point and then you zoom in or blow up that ball, you should see a line. And then you get kind of, in this case, on the left side of that line, a half space or half plane. Okay, and I put this picture here because the next thing I'm going to do is define half spaces in Heisenberg setting and also in Carnot setting. And so this is why we're interested in half spaces. We want to see, does the same thing happen in Carnot groups as happens in Euclidean space? Okay. So we define half spaces in Carnot groups as follows. Pick some cut E. We develop a set of E invariant directions, or directions that send characteristic function of E to 0. And then from there, we look at the set of invariant directions that also live in VI for some I. We say that a set E has constant normal if our normal vector is in fact constant. Again, this definition of constant normal agrees with the Euclidean definition of constant normal. And we say that a cut is a half space if it has constant normal, and also our invariant directions recover all of our layers or stratification from I equals 2 up to S. If you prefer to think in the Heisenberg group half space is defined as follows. We're looking at the inverse image of the set. So we can take a set K, which is a half space in R2, and the map P that goes from the Heisenberg space to R2, which is the quotient map by the center of H. And then we look at the inverse image of that. Okay. And it was proven by Franchi, Serapiona, and Seracasano in 2003 that if we have a set of finite perimeter in the Heisenberg group, then for perimeter E almost every X, every tangent of E at X is a half space. And so this result agrees with the one from Euclidean space that I showed in the picture. But this result is strictly for the Heisenberg group and not for general step S Carnot groups. And so still we have to know, does this result, this kind of the thing that we get in Euclidean space, still hold when we are in general step S Carnot groups? And I'm going to say a few more things to say kind of where we use, or where Franchi, Serapiona, and Seracasano was used in the results of Jigger and Kleiner, because this is kind of where we need our adaptations for general step S Carnot groups. So with our set of finite, locally finite perimeter cuts, we can also define a cut measure on our group, and a cut measure is defined as follows. So we take some compact set K in our Carnot group, and we want it to be true that when we integrate the perimeter measure evaluated at K with respect to our measure sigma, we get something that is finite. Okay. In addition to the cut measure, we can define a corresponding cut metric, and there's the definition of cut metric. And Jigger and Kleiner showed that if we take some map F that goes from a Cardinal group into L1 and is Lipschitz, then we can find a cut measure sigma so that the metric which is induced by our Lipschitz maps agrees with our cut measure. Okay. And then it's also going to be important for us to note that in addition to being able to dilate and translate our cuts, we can also dilate and translate our metrics. Okay. And much of the results happen in the metric side of things instead of in the cut. Okay, so this is kind of the main technical tool that Jigger and Kleiner proved in 2010 in order to show that Heisenberg Group does not by Lipschitz embed into L1. And you can think of this as follows. So you take some cut measure sigma, and you get its corresponding cut metric, d sigma. And inside of this limit, you're looking at the blowup of the cut metric. And you're saying essentially that you can find a measure which is supported on half spaces that is arbitrarily close to the blowup of the cut measure. Okay, so blowups of measures, blowups of cut measures, metrics, sorry, correspond to cut measures on blowups. And here, essential in their results and their proof technique was the fact that we have this correspondence, so we know when we blow up cuts, we end up, finite perimeter cuts, that we end up at a half space. So that was essential to the results. Jigger and Kleiner claimed that if the results of Franchi, Serapione, and Serracasano held for general Cardinal groups, then the result would immediately extend to general Cardinal groups as well. So here's the statement of the theorem by Franchi, Serapione, and Serracasano again. And unfortunately, this result wasn't able to be shown for general Cardinal groups, but Ambrosio, Kleiner, and Ladone showed a good enough result for what we needed. They proved that every finite perimeter subset, or for every finite perimeter subset E, and for perimeter E, almost every point inside of our group, there is some blowup of E that is a half space. So the important part here is they don't have uniqueness of blowups, but we know that we can find at least one half space. And I will say why that is enough in a minute. Another result by Ambrosio, Kleiner, and Ladone was an iterated tangent result. And this theorem essentially says, as you take tangents, things get better and better. So you take the first tangent. We don't know if we end up at a half space or not. But we know we only need to take at most mg, which is the dimension of our group, minus m1 iterations of tangent taking to definitely end up at a half space. Okay, so we need a replacement in that technical theorem of Jigger and Kleiner in order to be able to prove that Cardinal groups don't by Lipschitz embed into L1. The replacement that we choose is the following. So we're going to take sigma to be a locally finite perimeter cut measure on our Cardinal group. And we're going to choose a collection of cuts such that our collection is compact. It consists of all the constant normal cuts. It's translation and dilation invariant. And it contains all of our sigma generic tangents. And we're able to recover the main technical tool, except instead of taking cut measures that are supported on half spaces, we are taking cut measures that are supported on this collection F that we've defined. Okay. And I'll just spend the last few minutes kind of going over how we use this technical tool to show that Cardinal groups do not bilipschitsly embed into L1. So we're going to start by choosing a Lipschitz map F that goes from G to L1. And we know by the theorem from Jigger and Kleiner that we can choose a cut metric that corresponds to the metric induced by the map F. Okay. Then we're going to use the main technical tool. And we're going to start by finding a cut measure, we call it sigma 1, and a corresponding cut metric that agrees with our blowup of d sigma, so our original cut metric. Okay. And then we're going to iterate this process using our iterated tangent theorem. We're going to iterate it at most mg minus m1 times until we arrive at a cut measure that's supported on half spaces. And we also get a corresponding cut measure, metric, sorry. Okay. This cut metric that we get, it agrees with the blowups of our original cut metric. This means that it also agrees with the blowups of df, our induced metric, since our original cut metric and df agreed to begin with. Okay. Now we're going to add the assumption that f is not only Lipschitz but bi-Lipschitz. And this tells us that df is Lipschitz equivalent to the Carnot-Kerr-Theodori metric. Bi-Lipschitz equivalences are preserved under the blow-up process. So we get that this new metric that we came up with, d sigma mg minus m1, is bi-Lipschitz equivalent to the Carnot-Kerr-Theodori metric. And then we do a comparison. So we are taking an element z in Lie bracket G with G. We're finding the Carnot-Kerr-Theodori metric, or bounding the Carnot-Kerr-Theodori metric between the identity element in Z. The first inequality comes from the fact that we have bi-Lipschitz comparability. The second equality comes from the fact that this metric that we've come up with is supported on half spaces. And of course, we get that this distance is 0. We conclude that Z needs to be the identity element, and this tells us that our group was, in fact, abelian. Okay. So I think I'll stop here. Thank you.
Thank you so much for the introduction. Thank you to the organizers for inviting me and for organizing, especially our in-person organizer, Anna. So yeah, this is a joint work with Guy David and Antoine Julia. I'll talk mostly about some literature and then state one result and most likely not talk about the proof, but feel free to interrupt and ask questions. Okay, so for today or for the next 20 minutes, omega is an open set in the complex plane, connected and usually either bounded or it'll be the complement of a compact set E. And in that case, we think of it as a subset that has the point at infinity. And in that case, we also assume that E has positive capacity, which just means that sort of it gets seen by harmonic functions. And in this case, we can define an object called harmonic measure. So if you fix any pole x in the domain, harmonic measure with pole at x, it's a probability measure. I'll denote it by omega. It depends on the pole and the domain. And it's a measure which gives the following solution. So if you fix f, which is a continuous compactly supported function on the boundary of the domain, and you extend it harmonically inside the domain, then the solution, u sub f, its value at the point x in the domain is given by integrating the boundary data against this measure, which is harmonic measure. And if you haven't seen it before, it's not so mysterious. If you have a nice C1 domain, then harmonic measure is essentially just given by the normal derivative of the Green's function of this domain against surface measure. But for more rough domains, the representing object you get is a measure, not a function. Oh, and I should also mention, in the case that if omega contains the point at infinity, we want UF to be harmonic at infinity as well. So really the point at infinity is like an interior point. And lastly, okay, so omega is connected. So it's true that if you take two different poles, these two measures, harmonic measure with pole at x versus pole at y, they're mutually absolutely continuous. And so from the point of view of absolute continuity, it doesn't really matter which pole you choose. So we'll fix one, and the pole doesn't really matter in the end. Okay, and if you haven't seen harmonic measure before, there's a probabilistic interpretation. So if you fix a subset E and the boundary of your domain, then harmonic measure of that subset with pole at x is the probability that Brownian motion, or just the motion of a random particle moving in space, exits your domain omega through the subset E. So there's this absolutely wonderful picture by Matthew Badger. So on the one hand, you have harmonic measure as a measure which represents solutions to a PDE, and on the other hand, it's defined in terms of Brownian motion, sort of the exiting distribution of random particles in a domain. Okay. So if we fix a domain and we look at surface measure on the boundary, so you look at d-dimensional Hausdorff measure restricted to the boundary, where d is the dimension of the boundary. I'll call this surface measure. The sort of the name of the game here is how are harmonic measure and surface measure on the boundary related? The two most basic questions maybe we can ask are, when are these measures absolutely continuous with respect to one another, and when are they mutually singular? And just to state really quickly, why would you care about this? Well, on the one hand, absolute continuity of these measures is very closely related to boundary behavior of harmonic functions, which is important from the PDE perspective. But it's also sort of just interesting to think about how do Brownian travelers see the geometry of your domain, right? Because there's this probabilistic interpretation of harmonic measure. Okay, and I should mention we're working in the complex plane, and if it so happens that the boundary is one-dimensional, or more generally, if it's dimension n-1 in Rn, by today's standards, there's a very complete description sort of answering the questions above, more or less. There are answers to absolute continuity and quantitative absolute continuity by these authors here. And the punchline is that good geometry of a domain and its boundary are sort of necessary and sufficient in order to get absolute continuity. On the other hand, if D is not equal to 1, so if the boundary is not codimension 1 in the plane, the situation is somehow much less clear than the codimension 1 case. And this is what I'll talk about. Okay. But to talk about the story, I need two definitions. The first is the Hausdorff dimension of a measure. And I'll define it this way. So mu is just a measure in the complex plane, real valued. We'll say that the dimension of mu is the smallest Hausdorff dimensions of Borel sets F, where outside that Borel set F, mu has no mass. And I can give you an example which sort of illustrates what's going on. In general, the dimension of a measure as defined here is not the same thing as just the Hausdorff dimension of its support. Here's a good example. If you take your measure mu to be a bunch of Dirac masses centered at the rationals with weights AI, which are summable, then the definition above, if you take the set F to be the rational numbers, which has Hausdorff dimension 0, will tell you that the dimension of the measure is 0. But if you look at the support of the measure, it's the full real line, and this has Hausdorff dimension 1. So this is just some way of saying, like, where does the measure live, but not what is its closure. So this is the main point. And secondly, there's one phrase which will sort of just come up again and again, which is that the dimension of harmonic measure is less than the dimension of surface measure. I'll call this dimension drop of harmonic measure. A lot of the results I'll talk about say this, and I should say that this is a stronger statement than mutual singularity. So if this statement holds, if you have dimension drop of harmonic measure, then the measures are mutually singular, but it's stronger. It says harmonic measure sees a lower dimensional subset of the boundary. And then there's only one other definition I need, which is Alfor's regularity. So I'll say that a set E is D Alfor's regular. If you look at the d-dimensional Hausdorff measure of any ball centered on E, if that measure is comparable to r to the power d, for any x in E and r up to the diameter of the set. And just to give you a concrete example, the four-corner Cantor set, which is one of my favorites, is 1 Alfor's regular. Okay. So now I'll give some brief history of the problem we were interested in. It's selective. I can't say everything. There's a result of Makarov in 1985, which says if you take any simply connected domain, the dimension of harmonic measure is at most 1. So no matter if you take like a snowflake, which has dimension very close to 2 in the plane, harmonic measure only sees a set of dimension 1. And this was extended to a very general class of domains. Basically, you can take the complement of any compact set, and the same holds true in the complex plane. And this was due to Jones and Wolff in '88. And again, I remind you that, so if you fix some snowflake with high dimension, say a dimension bigger than 1, this says that dimension drop of harmonic measure happens, and so you have mutual singularity. There are also a large class of results, which I'll summarize as, for many Cantor-type sets in the plane, if you look at their complement, harmonic measure has dimension drop. This sort of started with Carlson in 1985, who proved it for the four-corner Cantor set. And this was continued by Makarov and Volberg, and later by Volberg, who proved the same conclusion for a large class of Cantor repellers. This just is some fancy way of saying Cantor sets which have some self-conformal structure. And more recently, there are works of Batakis and Zunic, which say roughly for a large class of self-similar enough Cantor sets, the same thing holds. But they use somehow different techniques which sort of move into higher dimensions, which is important. And lastly, there's a third class of results, which has to do with Alfor's regularity. And roughly they say, if the boundary of a domain is Alfor's regular, then you have dimension drop of harmonic measure. So there's a result of Jonas Azam in 2020, who proved that if E is D Alfor's regular for D bigger than 1, and I'll skip the other thing, then you have dimension drop of harmonic measure. And more recently, there's a result of Xavier Tolsa, who proved if D is between 1/2 minus epsilon and 1, and you also know that the boundary E is contained in a C1 surface, then you have dimension drop as well. And I separated these because these hold in higher dimensions, whereas the previous ones very much use complex analysis and conformal maps and things like this. On the other hand, okay, so all of these say they're a large class of fractal type sets where dimension drop of harmonic measure happens. There's a result going in the other direction, which is an unpublished construction of Chris Bishop, where he shows you can find compact sets in the plane of really small dimension for which surface measure and harmonic measure are comparable, in fact. But the main thing about these sets, I can tell you more about them if you wish, but they're very far from being Alfor's regular. They look like a bunch of circles replaced by smaller circles that are very far apart from one another. Okay. So there are a large class of results for which we have dimension drop of harmonic measure. And I think it's kind of interesting to tell you when does dimension drop happen. And I can tell you one mechanism which gives it. I'll call it something like consistent change in density. What is this statement? Okay, there's a little bit of technical math, but it says the following. You can find a constant bigger than 1, so that if you look at any ball centered on the boundary, there's some sub-ball B tilde, which is of comparable size. And if you look at these sort of density ratios, you look at harmonic measure over surface measure of the sub-ball, somehow it's far from the ratio of the bigger ball. it's either less than m inverse times the original ratio or bigger than m times the original ratio. And I had this picture that I was going to explain, but I don't think I'll do a good job. Basically, you can sort of convince yourself that if this happens, and you have like a really simplified picture of what's going on in a line segment, it says, you know, if you look at any dyadic interval, you can find another dyadic subinterval where the density of harmonic measure with respect to surface measure sort of changes a lot. And you can, I mean, it's not a proof, but you can sort of track this down to really small scales. And you'll see that harmonic measure has to concentrate on really small pieces of the real line if you do that in the simplified case. And so it's really just a geometric measure theory fact that if you have this property and you know that the boundary is Alford's regular, then you have to have dimension drop. This is just about measures. You could replace harmonic measure with a different measure and it still holds true. So this is one mechanism which implies dimension drop. But what implies consistent change in density, this weird thing where density changes a lot from scale to scale? I can give you one tagline, which is, it's morally true, which says that Brownian motion started from infinity prefers the outsides of the boundary. And there's one computation that I saw, which I think highlights this really well. If you look at, okay, so I'll take my domain omega to be the complex plane without the real segment from -1 to 1. And by means of a conformal transformation from the unit disk to this domain, you can actually compute explicitly harmonic measure on the boundary of the domain. So you can compute it. It's absolutely continuous with respect to arc length on the segment. And it has a density, which is sort of described by 1 over root 1 minus t squared. And so the density looks something like this. So here in blue, there's the line segment, which is the boundary of the domain. And red above is the density of harmonic measure with respect to surface measure. And you can see, right, that the density blows up near -1 and 1, the edges of the segment. And it says something roughly like, you know, if you start a Brownian traveler from infinity and you condition upon hitting the boundary on a small segment, you're way more likely to hit the edges of the segment than the middle of the segment. And this gives you something like consistent change in density, right? You have a set. If you look at density ratios in the middle of the segment versus the edges of the segment, there's sort of a huge discrepancy. And so, yeah, very briefly, this is sort of the mechanism which can give you a consistent change in density property. You can use this to prove that for self-similar Cantor sets, you have to have a dimension drop of harmonic measure, for example. Okay, so I threw a lot of information at you. I'll give you a quick summary with a picture, and it says the following. So if I graph on a number line the dimension of the boundary of a set between 0 and 2 in the complex plane, then for a whole bunch of sets, dimension of harmonic measure drops. In the full range, you have dimension drop of harmonic measure for self-similar enough Cantor sets. In the range between 1 and 2, you have dimension drop of harmonic measure no matter what. And for Alford's regular boundaries between 1/2 and 1, you have dimension drop as long as the boundary is contained in a C1 curve. And so it's sort of a natural question to ask, does this always happen? And what does it mean by always? You know, for which classes of sets do you expect dimension drop of harmonic measure? There are two sort of natural classes from the results that we know so far. One is for all dynamically defined boundaries, or boundaries that have some like self-conformal structure. And another natural class of sets are those whose boundaries are Alford's regular. And the result that we showed is sort of going in the other direction for Alford's regular sets. So this is our theorem. We have a construction, and it says the following. If you give me any dimension between 0 and 0.4, so kind of small, we can find a bi-Lipschitz image of a Cantor set in the plane. It's d Alford's regular. This is sort of like the main thing. So that if you look at the complement of this set and you look at the associated harmonic measure, it's mutually absolutely continuous with respect to surface measure, and the density is comparable to 1. And there's a last piece. If the dimension is smaller, say less than 0.2, we can guarantee that the set E is contained in the real line. So it's not too crazy from that perspective. And this answers the question before in a small way. It says that dimension drop of harmonic measure is not just about fractal dimension and Alford's regularity. Somehow there's like another mechanism which implies dimension drop, which is not just these two things. Okay, and there's a corollary, but I'll skip it. Okay. I have 2 minutes. I can't really talk about the proof too much, but I'll mention just some ideas for, okay, so I know some people are not experts, but there are experts. You can feel free to tune this out. That's totally fine. The main idea is you want to construct a set E so that this object called the equilibrium measure, mu, is both explicit and uniformly comparable to surface measure. Who is this equilibrium measure, mu? Well, by definition, it's the unique probability measure on the set E, where if you convolve this measure with the natural logarithm, you get a constant almost everywhere on the support of the measure. And why do you care about this thing? Well, it's sort of just harmonic measure in disguise. So if you look at the convolution minus this constant, it turns out that this is up to a constant multiplication factor. This is just the Green's function with pole at infinity. And so the equilibrium measure is exactly harmonic measure with pole at infinity. So it's just a different way of characterizing harmonic measure. Now, with this in mind, how do we construct the set E? Well, we take a sort of a modification of a usual construction of a Cantor set. So imagine you're constructing the middle thirds Cantor set by discrete approximation. So you start with 1 point, and you break it up in 2, and you continue this process. We do this, but at each stage of the construction, we just wiggle the points a little bit so that it's not self-similar. And we have to do this because we have to avoid this mechanism mentioned before that implies dimension drop, this like change in density thing. And so how do we avoid it? Well, the simplification is just that, okay, we're constructing a set discretely, and we essentially force the natural probability measure on the limiting set to be the equilibrium measure so that we know it explicitly. Computing potentials or like these convolutions on smooth sets is hard, so we do it on discrete sets. And what we do is we compute something that is somehow like a discrete approximation to this potential with the natural probability measure at each stage of the construction. And we want to do it so that this thing is very close to constant as you iterate down scales. The only way that you can sort of make this happen is if the relative distance between two neighbors at the points in the construction, so the relative distance between these 2 points versus the closest nearest neighbor is sort of much, much smaller. And this is what gives the ability to control this discrete potential. But with that, I'm more or less out of time, but I'll just remark, the result works in higher dimensions, but we don't get a Cantor type set. And it sort of leaves open an interesting question combined with the work of Xavier Tolsa, which I'll phrase in this way. Can you find a compact set in the plane, which is Alford's regular of dimension at least 1/2, for which surface measure and harmonic measure are comparable or even just mutually absolutely continuous? The work of Tolsa says that if you can find one, it's not allowed to be in a C1 curve. But with our construction, we can only get dimension up to like 0.4, so we don't know. But yeah, I'll stop there, and I'm happy to answer any questions. So there's this weird thing about like, in the complex plane, we can construct something in a line, and the important property is that in this like 2-point construction, the two nearest neighbors have a symmetry property, where the distance from one to the other is the same if you reverse the roles. And so if we wanted to do this in higher dimensions on a sphere, you want the same property. So you want points on a 2-sphere in R3 where the distance between like n points is exactly the same no matter which one you take. And this is like annoying. And so we have a way of circumventing this where we just like take a product of our one-dimensional example with a line, and it happens to work. But somehow this is like the key thing that was annoying. You might be able to do it, but we thought it was hard, so we did something else. The truth is that we optimize constants, and that's the best we could get. I really don't know. I have no idea. Yeah, I think the interesting question is whether you can get 0.5 or not. And I don't know if any of us have a strong feeling of whether it's true. Yeah. So if we try to do the exact same thing, there's this like weird problem about equidistribution of points on the sphere, which we didn't know how to like deal with. And so instead, our construction is different, where we take the same construction in the plane and we multiply it by higher dimensions. So it's like, or we multiply it by a sphere in higher dimensions. So it essentially looks like our Cantor set in the line, but you multiply by spheres. So it's a little bit of like cheating, but so it would be like a cylinder. So the thing that's hard in higher dimensions, so in the complex plane, we just want positive dimension. In dimensions 3 and higher, you want dimension at least n minus 2 plus epsilon. And so what this means is like if you could just get away with 2 points on S2 and R3, you wouldn't get a set which has dimension bigger than 1. So we need to be able to take n large or something like this.
Yes, so pardon the slight change from what was in the program as the title for this talk. I began to realize a little after the fact that perhaps I should make the research a little bit more expository and introductory, as there may not be so much familiarity with the field of decoupling. A somewhat emerging subfield within the realm of harmonic analysis. Thank you, Anna, for the introduction, and thank you to the organizers for the invitation to speak. Thank you to NAA and their co-sponsors for the opportunity to speak about my research. And let's get started. So the notation that will recur throughout this talk, the usual abbreviation for the exponential function with complex values for the argument. Schwartz functions are the only functions f that I will consider because I want to be able to invert via the Fourier transform. I want to be able to apply Fourier transform to the function f and then also invert it back. That will just smooth things over. Now there will be this distinction between frequency and time space, what's also known as phase space. So this is why I have points marked x and points marked c. The Fourier projection is the first point of notation that is very centrally used within the realm of decoupling. We have these various subsets S that will eventually, or very soon, be specialized to a certain category, not the mathematical category, just a category of certain types of geometric objects we want to look at. And notice that what is occurring is a Fourier transform is applied to F, and then you restrict, you project the Fourier transform to make it so that the support is now the subset S, and then you transform back. So in particular, f hat, the Fourier transform of f, vanishes outside of the subset S. Following this bullet point are the usual LP norms and the little L2 norm. And lastly, getting back to the so-called specialization of the subset S and bullet point 4, these hypersurfaces M, there will be hypersurfaces M that we'll consider, and the delta neighborhood will typically be the subset S that we'll look at. If you're wondering why these subsets are the ones that we need to look at, we'll get into that shortly. Okay, so the next question to ask, I think, would be, what is decoupling? You have some wave f that we are modeling as a Schwartz function, and we would seek information about f by studying the composite waves whose frequencies lie within smaller regions. So the subset S that we had on the previous slide, let's partition it into finitely many subsets Si. And in terms of the Fourier transform, we have a corresponding decomposition of the function f. Now, in the realm of L2, if we're taking the L2 norm of this function, then difference between frequencies is sharply noted. This is a phenomenon here that goes by the name of square root cancellation. And if you recall trigonometry from high school, square root cancellation was perhaps first introduced to us there, where if you take functions that oscillate in a completely contrary manner, right, the cosine and the sine function, then the resulting amplitude of the consequent wave will have something that corresponds to the Pythagorean theorem. And in fact, the Pythagorean theorem with standard unit circle trigonometry is what proves this fact here. But we don't have to go all the way back to high school for this fact. Well, maybe I should stay on the slide. We don't have to go all the way back to high school for this phenomenon of square root cancellation. It also shows up in probability theory with so-called randomized spaces. So if you take the so-called Rademacher functions that are defined on probability space consisting of binary sequences, then there is a square root cancellation that holds there, and it applies to all LP norms of linear combinations of Rademacher functions. So that's just an extra fact. But let's return to something that is more pertinent to decoupling, more immediately pertinent. Decoupling can be thought of in terms of exponential sums. They go right in hand, and you take any point, any sequence of points Cj that are in Rn, corresponding complex numbers Aj, and some ball B that is of yet unspecified radius. And we consider what are called the exponential sums. And decoupling produces results that look like square root cancellation. And this is a bound. And it is of interest to ask whether or not it is essentially a lower bound too. So there are cases where decoupling is in fact sharp. Trying to stay mindful of the time. Are there any questions so far? Okay, we're staying preliminary for now. This is good, no questions yet. Okay, one may try to generalize one to arbitrary LP norms. So instead of what we had on the previous slide, where, yes, so this is for general LP, and proposition 1.1 is an attempt to actually find some validity to the previous slide. So if we have P and R that are greater than or equal to 2, then this inequality was well known in the literature, the standard literature of harmonic analysis. And it follows from Plancherel's theorem, if we remember that, as well as the trivial L infinity bound. So P equals infinity. You just do the most natural thing there. And when you interpolate between the L2 and L infinity bounds, we would have this inequality, which tells us essentially the amount of loss that comes by way of trying to take the little L2 norm of the LP of the smaller parts, the so-called square root cancellation. Now, this is a postulate that holds under fairly general conditions for the SI. You may merely have them be balls or cubes with pairwise disjoint doubles. And whether or not this is in fact sharp, well, it is when the SIs are essentially all the same, but just moved along a fixed line and by the same amount of distance. That's crucial too. If you allow a lacunary change in the translation, then this would no longer be sharp. And that's where there would be opportunity for the decoupling phenomenon to occur, which we haven't gotten into that yet. Right. This is just a trivial decoupling, but we will get into decoupling unqualified in just a moment. Pay special attention to this exponent for capital N. That will change momentarily. Any questions? Okay. Before we look at decoupling, let's just motivate a little bit why that postulate might be true. The first equality is just a geometric series formula being applied, and this inequality is just decomposing into, or looking at the real part, rather, of the expression on the left of the inequality sign. And you can apply L'Hopital's rule right away to see that at 0, or very, very near 0, the value of the ratio of the signs would be essentially n plus 1 to the p. But it remains essentially that for this neighborhood that we can precisely calibrate as being of length 1 over n, centered at 0. And so if you just take the integral over that interval, then we automatically obtain a pretty high lower bound. And this n to the 1 minus 1 over p, when you multiply it by the value of these LP terms, they're all essentially 1, but you have n many of them. And so this would together, the product would be n to the 1 minus 1 over p, and that would now match what we have on the other side of the LP norm of f. So this is an example of why the sharpness phenomenon occurs when we have the equidistant translates as being our sets SI. Okay, so keeping it moving, we should get to the definition of decoupling. Decoupling takes the same setup that we had before, and everything is the same as on one of my previous slides, except that the exponent changes, as I was intending to point out before. Instead of having 1 minus 1 over p, and then the 1 over r after, the 1 minus 1 over p has been reduced to something that is always smaller when p is larger than 2. Now the 1 minus 1 over p is being substituted, or having substituted for it, this 1/2 value. And that presents a lot of gain for many problems that crucially depend upon this deconstructive wave phenomenon. And concerning the C, we allow there to be at most n epsilon dependence there. And whenever this inequality holds, that is definitively LR-LP decoupling. Typically, R is 2 or P. And so when R is 2 in particular, we're calling that little L2 decoupling. Any questions? Okay. So this field of decoupling was pioneered first by Thomas Wolff, and he was able to obtain limited results for the cone, the two-dimensional cone. So taking Fourier projections of along delta neighborhoods of the two-dimensional cone. And for him, he obtained decoupling, the decoupling inequality that was just given to you for the range p greater than 78. That's much larger than the optimal range, which would be p larger than or equal to 6. And very recently, in 2014, John Bourgain and Cyprian Demeter provided L2 decoupling for the full range of p for the cone, but even more essentially for the paraboloid. So their proof started with the parabola, and from there were all sorts of surfaces that they were able to immediately derive optimal results for, including the two-dimensional, rather n-dimensional cone, so 2, 3, and higher dimensions for the cone. But also they were able to prove decoupling, optimal decoupling for hypersurfaces of so-called positive definite second fundamental form. So these would be hypersurfaces where the principal curvatures are all positive. So locally, they look like spheres. And yes, John Bourgain and Cyprian Demeter provided the optimal decoupling for those hypersurfaces and many others too that I won't get into. So now, what is this theorem telling us? Well, if we just stick with n equals 2, so the parabola, not paraboloid, you take the parabola and you restrict it to the interval -1 to 1, let's say. It just has to be a compact interval. We can take -1 to 1. And now the -1 to 1, you want to divide it into subintervals of length delta. Let's say delta to the 1/2. That's what I have on the slide. So sublength delta to the 1/2. And for each of those subintervals, you have a corresponding Fourier projection. And these are the p n delta taus that I have here. And so those occur on the right side of the inequality. And for any function f that lives on the frequency side within delta of the parabola, this will be true. There is a corresponding result concerning the arc length measure. You could think of this as being an inequality that pertains to that gives a bound for the LP norm of the Fourier transform of the arc length measure for the parabola. And that notion, that measure theoretic notion, extends to the surface measure for the paraboloid in higher dimensions. Feel free to interject with any questions or raise your hand. I'll be looking. There's not too many of you out there. So. Now, in terms of exponential sums, I just wanted to give the result, but we don't need to spend much time here. Okay, now why might people not within the specific realm of decoupling care about decoupling? Since 2014, there have been many substantial applications of decoupling that I wanted to give to you here. I know that there are maybe mostly fractal geometers in the audience, so notice that towards the bottom. To my knowledge, the best progress that exists at the moment for the Falconer distance set conjecture was secured by way of decoupling. And it's pushed that barrier all the way down to 5/4 for the plane setting. Right, and concerning why decoupling might apply, well, there are so-called spherical averages that come up pretty soon in the Fourier analytic approach that was developed by Matilla. And so for those spherical averages, you apply decoupling, but for the sphere. And the sphere is one of those hypersurfaces that locally looks like paraboloids. So the John Bourgain-Chyprian-Demeter theorem extends naturally to those surfaces. Okay, there are connections to number theory in addition. So if you take a system of equations of this form, just a standard system of Diophantine equations, then you would want to assess the number of solutions to the system. And it was conjectured since the 1920s that there would be roughly this many solutions. It's an upper bound that is known to be essentially sharp, except for the n to the epsilon. It's still hypothetical that that can be removed, but ignoring the n to the epsilon, this was conjectured to be the sharp bound for the number of solutions to that system of Diophantine equations. Okay, why would this connect at all to decoupling or even exponential sums? Well, that is the gateway, actually. You could write that same number that counts how many solutions there are to the system as an exponential sum. And it's because of the orthogonality properties of exponential sums along the flat torus, or the cube of length 1. And so as soon as you have that integral representation, then this would be the decoupling, or the, yes, decoupling that we would want to write. I'm using exponential sum inequality and decoupling interchangeably, which is forgivable. And this is the theorem that was proven within the past decade by Bourgain, Demeter, and Larry Guth. So just wanted to present it for curiosity. I should start to wrap up. We're getting close to time. So concerning possible extensions, let's look at how we might build upon the work of Bourgain, Demeter, and also Bourgain, Demeter, and Guth. So you can take the curve that is fundamental to the so-called Vinogradov system, right? So if we go back, this system of equations, just focusing on a single row of variables, right? You have x to the 1 power and then x to the 2 power all the way up to x to the n. That can be thought of as representing a hidden geometric object, what in this case would be the moment curve, defined as t goes to t to the 1, t squared, all the way to t to the n. So it's mapping from R1 to Rn. And you can actually extend the moment curve into a full-blown hypersurface in Rn by taking phi, which we're thinking of as the moment curve. And here I wrote out some of those values for n equals 5. But then you extend along the various derivative vectors by using SI parameters. Another way of looking at this is that you're taking the sequence of Frenet boxes. If you're familiar with curve geometry, these moment surfaces look like Frenet boxes that are arranged along the curve phi. And there's the decoupling that we have for p between 2 and 6 for these Frenet boxes. Okay. So it wasn't my intent to go through every slide. Just wanted to have enough in case of questions or in case I had more time. But I think I'll just end with this slide. So there are more decouplings that have been derived, that we've derived. It uses the standard tools of rescaling, approximate surface decoupling, and iteration. And there were the real analytic surfaces of evolution that were shortly after discovered in 2016. And then the developable surfaces in R3. These surfaces model the two-dimensional convex hypersurfaces of finite line type. And so if you obtain this decoupling, then the decoupling for the two-dimensional convex hypersurfaces of finite line type, it follows directly after. There's work, unpublished work as of yet, that divulges this. And then should also mention that Li and Yang were able to prove decoupling for smooth hypersurfaces in R3. But whether decoupling is possible for hypersurfaces in R4 and higher, we of course assume that it is, but that yet remains to be done. So perhaps some of the methods that go into this proof would be useful there. So let me stop there. Oh, I also have interesting pictures. I didn't mean to go this over time. My apologies. But yeah, thank you for the talk, for the opportunity. So the surfaces that were left to be proven, or to have decoupling proven for, which Bourgain and Demeter did not get to, would be the surfaces that have vanishing curvature. And so both the moment surface has vanishing curvature, but of course these surfaces all do. A standard example of the real analytic surfaces of revolution would be the torus. The torus, of course, has vanishing curvature at the top and bottom. And so this is what has had some work done, and much more work remains to be done. Sure. Yes. For example, the moment surface actually is singular when all of the SIs are 0, or even if one SI is 0. Yeah, at that point, things like principal curvatures begin to, well, the non-zero principal curvature actually blows up, for example. Also, even more fundamentally, you just don't have a tangent plane. Because all of the SI tangent vectors right. Sorry, I'm blanking on what happens, but essentially, from what I recall, yes, just the tangent plane, it becomes degenerate. You don't have a tangent plane there. Yeah.
But I guess,
and
in general,
right. Yes, there were more. There are more surfaces. So for the two-dimensional Cantor set, decoupling has been proven for that. and Chipre and Demeter was able to prove a result for the one-dimensional Cantor set, or the Cantor set in one dimension, where there is no dependence upon n. Or rather, instead of dependence and the decoupling constant being related in terms of sort of the length of your neighborhood, the width of your neighborhood, there Demeter was able to rewrite the dependence as depending just upon the number of sets you were taking. So this was something that also didn't necessarily seem explicit, but when we moved from the general formulation of decoupling to decoupling for hypersurfaces, there was this intuitively observed fact that was left implicit that delta would now essentially, a power of delta would now be the number of subsets that you would have. But if you, and that was simply because all the subsets had the same dimensions, right? For the parabola, for example, well, those were all subintervals of length delta to the 1/2. But it remains a conjecture for the parabola. Demeter was able to prove it for the Cantor set in one dimension. Whether or not, say, for the parabola, you could take subintervals of various lengths and instead just have the dependence for the decoupling constant be in terms of the number of those subintervals, right? Instead of like whatever you might take for the neighborhood width, maybe you'd have to take the minimum neighborhood width or minimum subinterval length with this this version of decoupling. That would be quite lossy.
So I'm going to start with non-local perimeter, which is measuring things. And this was introduced by Caffarelli, Roquejoffre, and Savine in 2010. And we defined the sigma parameter of a set E for sigma between 0 and 1 to be the double integral over E and E complement of the following kernel, 1 over distance between x minus y to the n plus sigma. This could be related if you've seen maybe fractional Sobolev spaces to the norm on the characteristic function of E. And the thing that I need you to remember for the sake of this talk is that it's all about integrating and caring about points where one is inside the set and one is outside of the set. All right? And just in case nobody's seen this before, to motivate why this is a perimeter, the first thing I like to think of is when is this integral integrating something big? It's when I have a point x and y where one is inside and one is outside, but they're close to each other on the boundary. So we are emphasizing the boundary in our definition. And the second thing is to know is that when we multiply this by 1 minus sigma, if we take the limit as sigma goes to 1, this converges up to a constant to the standard perimeter. And in case you were curious, if you send sigma instead to 0, it actually converges to something related to volume. So it's kind of funky, a lot of fun, relatively popular in the last few years. And this can also be done for relative perimeter. So in that case, we're doing integrals over sets in E and E complement relative to omega. And the whole idea is we're just ignoring those relationships where the pair of points, both points are outside of omega. Those are the ones that are not interesting, but we can think about this relative perimeter. And that's nice because it motivates a notion of local minimal surfaces, maybe a plateaus problem, where we're not going to define a boundary. We're going to define a complement because it's non-local and we see everything. So if you define a complement, you can say that you're locally minimal with that complement if you have the same complement, but you're the smallest relative perimeter. And minimum surface exists. They're smooth up to dimension n minus 8 for sigma near 1. So we have parallels to local minimal surface theory. We also have a notion of fractional mean curvature found by taking the first variation. I'm not really going to go into this too much today, but that's the formula in case you're interested. It has nice convergence to standard mean curvature when sigma goes to 1. And we have that fixed volume minimizers have constant mean curvature. Minimizers in the previous sense had 0 mean curvature. Okay, So we have this nice perimeter. We can associate perimeter in the local sense. It used to be just like, oh, how big is the boundary? Non-local perimeter, I should have said, is defined for relatively nice surfaces because we need that integral to converge. So we usually assume C1 alpha, C2 alpha if you want to have a notion of mean curvature. And this feels like we have a bit of a gap because you're like saying essentially what's the surface area of the boundary in a non-local sense. But I'm really requiring that I am a boundary. I need to be enclosing some set on the inside. So it was proposed that maybe there's a bit of a gap there and that we can extend this to the situation where we don't have a boundary, where we're just a hypersurface maybe, or maybe in a moment we'll go to some sort of a manifold of an in-between dimension. And so I'm going to come back to this idea. We're thinking about one point inside my set, one point outside of my set. But why do I think about this pair of points when instead I can think about the line connecting them? And what we'll notice in this picture, I have borrowed this shamelessly from my collaborator. We have lots of options for pairs of points where one is inside and one is outside. But notice that most of the time, the number of times this line crosses the boundary is odd, which is very useful for me, right? The only time I can really create an even number of crossing, if you look at my x3, y3 pairing, kind of over here, you notice I had like a point of tangency. And that seems pretty unlikely for most of the time that I take a point inside and outside. It's going to be hard to create, so I'm pretty soon going to ignore things like that. So this is the definition which was proposed by Proni, Podioulis, and Seguin in 2018. So if I say xy is the line segment containing x and y, connecting them, and I have a hypersurface, I'm going to first define this set of crossing points, calligraphic x of s, to be the set of points in Rn cross Rn where the line segment connecting them intersects my surface an odd number of times. And then once I've done that, we can find this definition for the sigma area of my bounded surface relative to a set omega to be 1/2 times the integral over this set of pairs, which actually corresponds pretty well with the definition I had before, except now I don't have to have an inside and an outside. There's a maximum in the numerator, but the denominator looks pretty much the same. And the maximum is really there just to make sure everything is finite. If I said my set is bounded, if you take omega big enough, you can ignore the maximum, it can be 1. All right, and delightfully, we have the same limit as we had before. Everything is feeling good and it's extended. They also, I should say, did a nice first variation. They have a notion for mean curvature. It's a little messier than the one that they had previously, but it's workable. Lots of options to take that from that. All right, so okay, we did n-1, but we have measures of objects in Rn that are not just n-1 dimensional. So let's see if we can get a little better. Our next step, other than n-1 dimensional, is to do maybe a curve, maybe a nice C1 curve, C1 alpha curve. And in that situation, we can think, okay, first, we actually know what that should be if n equals 2. If n equals 2, your curve is an n-1 dimensional surface. Sort of. And so we say, okay, we had line segments before. What should we do instead of line segments? And the whole point that I really appreciate about line segments is that when I take my line segment and my surface, before I got an intersection, that most of the time was just basically a set of points. Now I'd kind of like this to be happening in general. So I have my one-dimensional shape. I'm going to intersect it with something. The thing I need to intersect it with should be n-1 dimensional. And then I say, okay, and now what's the analog of my line segment? Well, my line segment secretly was a disk. It was just a one-dimensional disk. And so now we're going to do n-1 dimensional disks intersecting with my little curve. And so we set this calligraphic D to be equal to the set Rn cross unit vectors in Rn cross R plus, where each of these 3 components is going to tell me something about my disk, essentially. And so for a triple in this set, I define the corresponding disk, D of that triple, to be the set of points that are of the form P, that's the center, plus Xi times V, where Xi is a length that's less than my radius, and V is in a direction which is perpendicular to my W. So basically, if I have a disk, I need to know where its middle is, and I need to know what direction I need to not go in, and I can go in any other direction, but no more than R amount, or like less than R amount. That's my plan. And it's somehow very important that we have this nice description of the disk, because at some point you have to start doing integrals, and you need to make the set a little bit concrete so that you can actually understand what's going on. And so we define, I said before, I don't like even intersections, I don't want infinite intersections. We define calligraphic D sub omega for my curve C to be the set of triples, so that the intersections between this corresponding disk and my curve is odd, and I'm going to avoid the need to have that maximum anymore, and I'm just going to assume that the boundary of my disk somehow has a point within omega, just to make sure I didn't escape. And then the following function is my length, and it can be worked out that it corresponds to that area function that I had when I did my n equals 2 situation for hypersurfaces. So now hopefully you're like, okay, cool, we did n equals 1, n equals n minus, or my dimension is 1, my dimension is n minus 1. Let's find out what's happening in between. And in the meantime, I'm going to tell you that, okay, it also works for zero-dimensional things. So now I have to branch out. We already have the idea of disks. We have the idea that we want our disks to be the correct dimension to make my intersections good. So it should be n minus k dimensional disks. And things get a bit more complicated, because how do you describe your n minus k dimensional disk? And so here's where it became useful to be like, okay, so I'm really thinking about, you can either think about the direction that sort of you're span the directions that are contained in your disk, or you can think about the perpendicular space. And so our perpendicular space is k-dimensional. And we're going to describe that k-dimensional space in terms of simple unit k vectors, which, if you haven't thought about these in a while, these are, k vectors are multilinear maps, widgets of vectors. Simple just means that it can actually be represented, this map can be represented in terms of one of those wedges of k many vectors. And then I'd like it to be unit length, because I don't want to have to worry about scaling. And the most important thing is that this space, by thinking about this analog, can be seen as a double covering of the space of Grassmannians, k-dimensional Grassmannians in Rn. So this is describing my perpendicular space. And now I have a very similar definition to my space of disks, or the space that I'm using to describe my disks. And so for a triple in that space, P omega R, I'm going to set my corresponding disk, start at the point. You can go out in any direction V, which is not in the span that's created by my k vector, and up to R amount. We're feeling good about the disks? Okay. And then once more, I would like this intersection with a disk to be odd, and I want to not be too far away. So let's have a boundary point contained within omega. And so in the case where omega is really big and really contains my set M, we have proposed this definition for a k-dimensional measure. I should be honest, it's not technically a measure. It doesn't, I think, satisfy the additivity property, but it behaves like a measure in that you can sort of use it to see how big things are. And so it's the following integral. We're integrating over the radius to the appropriate power. This dimension of my Hausdorff measure looks kind of funny, but it's really just coming up from the fact that I have a point in Rn, the size of the Grassmannians, plus 1 for the radius. So it's really just the size of the space of disks. And basically, once more, it was really key that basically we can cast out all of these disks that have infinite intersections or even intersections and just stick to the odd ones. And so what we managed to prove is that as sigma goes to 1, in the limit, the measure of a set M converges up to the appropriate constant of the Hausdorff measure of that size set. And so this is great. We're very excited. Now we're thinking about what options to go with. So we'd like to do that first variation argument that happened for the previous two sort of notions of size, and then see what options can happen next, sort of in analog with minimal surface theory. And I think I have some time, so I'm going to just give an idea of the proof. which is only one slide. So it's just sort of an advertisement for what's going on because it gets a little computational. And the main idea is that here we're asking you to integrate over a very strange set, right? So we need to go from this strange set to something that's a little bit more easy to work with. And so we're going to try to describe the potential disks that could happen in terms of more concrete objects that are easy to integrate over. So I'm going to define the set W, which is the set of pairs where we have a unit vector, that's my calligraphic U of Rn, and a simple k vector. I want my unit vector to be perpendicular to the span of that k vector. And I'm defining a map C, which goes from the closure of my manifold, cross with my W, cross with R0 plus, so this is strictly positive numbers, cross with R plus, those can be 0, to Rn, to basically to my set of disks, Rn crossed with my simple vectors crossed with R. And the way I'm going to define the map, the idea is I'm associating the disks that I care about. So if I have a disk that has an odd number of intersections and it's intersecting with my manifold, well, there's some point on the manifold which the disk touches. So I'm going to start at that point, and in some direction, I should be able to find the center of the disk. So that direction that I need to go in is my A. How far do I need to go in that direction? That's going to be my C. And that C should necessarily be less than R, because I can't go more than the radius to the center. And then in my W set, we have the omega, and that's really going to be the space that I am perpendicular to. So the nice thing is that I have this map, and because I have this this sort of notion of how to associate disks that intersect my boundary with this nicer set, I can say, well, the odd disks are contained in the image of the appropriate set, which is easier to handle. And in fact, the difference between the image of this set and the odd disks is very small, because if you're intersecting, you're probably intersecting an odd number of times. And so the key idea, this is a rough argument from just sort of the proof that this measure should converge, is that you start off with the integral that I had in the previous slide, and you do a nice change in variables that, of course, takes a few pages. And then a few pages later, you have that this is a nice upper bound, or you can get it tighter so that you don't need the less than or equal to. An integral over M, which is a manifold. 0 to 1 also feels pretty good. W, a little weird, but okay. And a nice other integral for my R. And so we can immediately bound this. I've got sort of a nasty volume form thing, because these are sort of vector-like things. So because W is compact, we just get the size of W, where this is, I'm going to say, the dimension of it. We can bound this fact that I'm integrating over M with just whatever its actual size is. And then I get something that, with a bit of nice mean value theorem, actually tends to go away as well. So it's a lot of this change of variable arguments and, like, sort of carefully thought out, I hope, associations of my disks with nicer, more workable sets. So that's my advertisement. Thanks so much for listening.
So I have to preface this by saying that I was completely unaware of Cornelia's work up until 20 minutes ago, 30 minutes ago. And there are some scary similarities. I was superficially familiar with non-local perimeter, but I was under the impression that the connections to this work were, well, superficial. I'm second-guessing that now, but we're going to have to talk about that afterwards. All right, so with that, hello everyone. So I'd like to start by thanking Anna, Max, and Mariana for organizing this session, and the AWM for their role and their support. Also like to thank Stefan Steinerberger for all his ideas and suggestions throughout my work on this project. That's a lot of people to thank, and it's a pretty short talk, so I think I'll skip those thank yous. So diving right in, The starting point is going to be this observation of Stefan from a paper last year. So he noted that if omega is a C1 bounded convex set in Rn, and if x and y are boundary points of omega with normal vectors nu of x and nu of y, then these vectors are roughly orthogonal to the line connecting the two, so to the vector x minus y, whenever x and y are close with respect to the Euclidean distance. Now, if this had said with respect to the Riemannian distance on the boundary, this would be trivial simply by the continuity of the normal vector field. But the idea is that if we have a set that boson in itself, it's not convex, then you can have 2 points that are very close in the Euclidean sense, but there's a bunch of boundary between them. And so you'll have these vectors that point in very different directions, even though in the Euclidean sense the points are very close to each other. And he showed actually that this property characterizes convex sets in a very quantitative way. So under the same hypotheses, we have this double integral over the boundary of omega with respect to surface measure is greater than or equal to some explicit constant times the surface measure of omega. And so that integrand is absolute value x minus y dot nu of y times x minus y dot nu of x all over norm of x minus y to the n plus 1 power. And moreover, equality holds if and only if omega is convex. And so the way that this is capturing the property articulated in the observation is that notice that we have this Euclidean distance in the denominator here. And so if we want this right-hand side to be small whenever, to be small in general, will require that whenever x is close to y in the Euclidean sense, it's also the case that nu of y is roughly orthogonal to x minus y, and nu of x is roughly orthogonal to x minus y. So this really is restating this in a formal and quantitative way. And so the motivating question that I'm going to adhere to in this talk, and it's not even my question, but we'll get into the history of that later, is whether there's an anisotropic analog of this inequality. And what I mean by that is another way of interpreting the inequality is saying that convex sets are somehow very insecure. They don't like to look at themselves up close. The integrand is such that it gets very large when you have two pieces of boundary that are facing each other like this, one here, normal vectors pointing in opposite directions. And so, where was I going with this? So what I've been thinking is, all right, do we characterize a different class of sets if instead of just hating all directions whenever the two pieces of boundary are close to each other, what if we privilege some directions over others? Instead of family of convex sets, do we get something else? So to completely go off the rails, I'm going to start with an observation that is seemingly unrelated, and it's the following. So if E is a set of finite perimeter, then for almost every x in the reduced boundary, that's the set of points where we have this unit normal vector field, outward pointing, we have the following identity. So this integral over the reduced boundary with respect to n minus 1 dimensional Hausdorff measure is constantly equal to the n minus 1 Lebesgue measure of the unit ball in Rn minus 1. And so I'm going to abbreviate that, alpha n minus 1. We'll see that constant a few times. And what do I have here in the integrand? Well, it's exactly what we had on the previous page, except I've dropped those absolute values. So in dropping the absolute values, the inequality became an identity. Notice that if I just integrate again over the reduced boundary, I'll end up with equality. This will be equals alpha n minus 1 times the measure of the boundary. So I'm showing this is it does give immediately an identity instead of an inequality analogous to the previous page. And so the way that this works is that there's this systematic cancellation that goes on when you drop the absolute value. When you have this absolute value, every time you're integrating over a non-convex set, you get the systematic overcounting, and just something as simple as dropping the absolute value turns that overcounting into just the right amount of cancellation for an identity. So again, I'm not touching this motivating question for now. I'm going to leave it on the back burner, but we'll come back to it soon enough. All right, so I thought to myself that this systematic cancellation, the structure of sets of finite perimeter is stronger than we need in order to obtain this. So I thought to myself, what is the property that is going into the proof here? And I came up with this definition inspired by some weird algebraic topology, probably the only time I will be inspired by algebraic topology. That's no offense to the field, I just, yeah, whatever. So given an n-1 rectifiable set sigma and a measurable unit normal vector field nu on sigma, we'll say that the pair sigma nu satisfies the orientation cancellation condition, or OCC, if at almost every point we have this funny identity for almost every direction. So here I'm summing over all points y in the line through x with direction vector omega intersected with our surface sigma. And what am I summing? I'm summing the sign of the dot product of omega with the normal of vector at y. I'm requiring that sum to always be 0, or almost always be 0. And I think it helps to look at a picture here. So here I've drawn this nice n-1 rectifiable set, so one rectifiable set in the plane. I fired a typical line through the set. Let's imagine it being directed up and to the left. And notice that there are 1, 2, I can't see from this angle. 1, 2, 3 vectors pointing the same general direction as the line up and to the left, and 1, 2, 3 pointing down and to the right. And so that's what the orientation cancellation condition is requiring, that whenever you fire a typical line through the set, you have this happen. There are an equal number of vectors pointing in the same general direction as the line as the number pointing in the opposite sort of direction. My advisor says to always start with the simplest possible example, so maybe we should be keeping in mind this nice trivial example here, where notice the extra structure that I was trying to abstract out was that not only do we have this orientation cancellation condition occurring on the boundary of the set of finite perimeter, we actually have like alternating signs. Notice that these are pointing like upper left, lower right, upper left, lower right. And it's that alternating signs that I wanted to get rid of, or not get rid of, but wanted to generalize since that's not what was needed, although that will come in handy later, so we'll stick a pin in that. So to recap, the first heuristic is that, when we fire a typical line through, we have the same number of vectors pointing in the same general direction as the line is opposite. Another heuristic is that nu behaves like an orientation vector field for the rectifiable set. The concept from algebraic topology that I alluded to is in fact how algebraic topologists like to talk about orientation of cell complexes, and this was my best attempt to capture the property of orientation that I wanted these sets to have. All right, so with that definition, we can restate theorem 1 almost exactly, except, there we go, except I've replaced our set of finite perimeter with its outward unit normal vector field just with this pair sigma nu satisfying the OCC. So if sigma nu satisfies the OCC, then at almost every point in sigma, we have this identity, the same identity as before, except I'm integrating over sigma, and instead of nu e, I just have nu. And so there's a geometric interpretation here. It's a little bit strange, but if you imagine sigma as being like a semi-transparent surface, so something like a plastic shopping bag. I hadn't seen one in so many years until coming here to Florida. But I guess they still exist. So imagine this semi-transparent surface. No matter where you stand on the surface, you look all around you, and you see some pieces of the surface that are facing toward you and some that are facing away from you, where that toward or away is determined by whether the normal vectors are pointing in your general direction or away from you. It's saying that the net quantity of surface area facing toward you minus surface area facing away from you is almost everywhere constant. It almost doesn't depend on where you stand, and in fact, it doesn't even depend on the surface sigma. It's just this universal constant, and that constant actually is negative alpha n minus 1. Okay, so why is this a reasonable interpretation? It sort of falls out of the proof, and so I'm just going to give a very brief heuristic proof. So here I've drawn an actually relatively simple set, C1 bounded set here. And so I've picked a typical point in the boundary, and I've partitioned Euclidean space into double cones with vertex at x. So x is right there. And what I do is I look in each of these double cones, and I look at each of these slices of the double cone by our surface sigma. And if I write the integral from the previous slide, or 2 slides ago, however many slides ago it was, if I write that integral in polar coordinates centered at x, roughly what I get is that each of these little slices is going to be counted as plus or minus 1 little unit, where the plus or the minus is determined by the direction that the little piece of surface is facing relative to the axis of this double cone. So here I'm counting, let's see, little positive piece, so plus 1 unit, minus 1 unit. Everything in here just sums up to 1 unit, and that's because of the orientation cancellation condition. So the OCC is precisely giving to me that in each double cone I get plus 1 unit, plus 1 unit, plus 1 unit, plus 1 unit. And when you add it all up, things are normalized in such a way that you always get alpha n minus 1. So that's the proof. And so the thing that I didn't necessarily need, I didn't need these alternating like blue, red, and then on the other side, blue, red, blue, red. I just needed them to sum up such that you had one more blue than red in every double cone. So that's what the orientation cancellation condition was doing. Okay, so about 20 minutes after I post this on the archive, I get an email from Max Goering. It's several pages long, and it asks me all these questions. I'm not joking, that's really what happened. One of his questions was to the effect of, can you plug in an arbitrary function into this integral? It seemed like there's some sort of Cauchy integral formula thing going on. I'm not doing his question good service, but it was something to that effect. And so I thought about it a bit, and this was my first attempt at an answer. So if f is an odd function on the sphere, an odd L1 function, and if sigma nu satisfies the orientation cancellation condition, then we have this integral identity for almost every x in the surface. And that's integral over sigma of f of pi y of x. So that's the radial projection of x onto y. So f of pi y of x times x minus y dot nu of y all over norm of x minus y to the nth power. Integrating with respect to surface measure, that is going to be equal to this integral here. So it's an integral over a hemisphere. I'm going to abbreviate this now. So what I'm doing is integrating f over a certain hemisphere. And what's that hemisphere? It's the hemisphere behind sort of the normal vector nu of x. So if this is nu of x, I'm integrating over this hemisphere here. So the reason that I am calling this sort of an anisotropic version of the singular integral identity from before is that I'm thinking of f as a weight on the set of directions. So previously, what did we have in place of this f? We had y minus x dot nu of x over norm x minus y. And that the weight there just so happened that in some sense it weighed all directions equally. You had this extra dependence on nu of x, so it was a whole family of f's, and they just so happened to weight things sort of appropriately. So this is maybe one anisotropic version, but Max was unhappy with this. He did this sort of heuristic divergence theorem proof and said that we shouldn't need this to be odd. Well, divergence theorem doesn't make sense on just like any typical rectifiable set satisfying the OCC. This applied for sets of finite perimeter. And so we worked through and saw if we could adapt the proof to sets of finite perimeter without the assumption that f was odd, and indeed, he was right. If f is just any L1 function on the sphere, and if E is a set of finite perimeter, then we get the same integral identity as before. Now we're just integrating over the set d star E instead of sigma. Oh. Sorry, radial projection of x onto y, so that's x minus y over norm x minus y. Yeah, there's this law of conservation of bad notation going on here. Just nothing I did could make this better, and I eventually convinced Max that there's no good notation. We went like full circle, and this is the notation that we started with, and the one that he had complained about, so my apologies. So, all right. So the reason that we need a set of finite perimeter in order to drop the assumption that f is odd was that it goes back to that extra structure, the alternating signs of the vectors as you fire your directed line through the set. It's just somehow necessary for this cancellation to work appropriately. All right, and so now we're sort of, going back into some anisotropic stuff that we had completely deviated from. We're going to slide into some corollaries, and one of them is going to be the anisotropic Steinerberger inequality. So I wonder which one it's going to be. Looks like it's not this one. So let Rj of mu be the J3 transform of this finite sine-Borel measure mu. Then we have this identity here. So for any set E of finite perimeter with jth component of the unit normal vector field denoted by nu Ej, we have the following. So the sum from j equals 1 to n of the J3 transform of nu Ej n minus 1 dimensional Hausdorff measure restricted to the reduced boundary, that sum is almost everywhere equal to 1. And so, put more simply, the dot product of the Ries transform operator with the Gauss-Green measure is almost identically equal to 1. 1 over pi, actually, I renormalized the Ries transform so that we got 1. I think that, there's truth, beauty, and usefulness in mathematics, and you get like any 2 out of 3. I think as written, renormalized, it's pretty beautiful. So I'm kind of hoping that it's not useful. All right. So second corollary. How am I doing on time? Not too bad. Second corollary is this sort of, I can only describe it as like a generalized Gauss law of electromagnetism. Gauss's law of electromagnetism would tell us if I have some electromagnetic potential either centered inside of a nice closed bounded set or outside of a nice closed bounded set, you either get this quantity up here or that quantity down there. But, two things it doesn't do. One, it only applies when, electromagnetic fields are, to my knowledge, isotropic. There's no special direction in the universe. So whether or not this is actually useful, I have no idea. But in addition to being able to sort of plug in an arbitrary function f here and get this sort of Gauss-type law, we also are able to treat the case that x is in the boundary. That's precisely the theorem from, say, the last page or 2 pages ago. So I don't know, that seems useful. I would have thought that somebody had already proven this sometime in the past 200 years, but I couldn't find it anywhere. But in any case, I definitely would like to know if anybody knows about, say, this middle line here, whether they've seen anything like this before. But all right, lastly, I said there was going to be a corollary that tied back into where we started. So this is finally sort of an anisotropic type convexity characterization inequality. So let G be an L1 function on the sphere across the sphere. And suppose, okay, this weird hypothesis that the L1 norm of G in its first argument is constant as a function of its second argument. Then this isoparametric problem is solved precisely by the convex sets of finite of perimeter P. And what's this problem? So we're taking the infimum over all sets of finite perimeter with perimeter P, all bounded sets of finite perimeter P, of this double integral with respect to surface measure. And what's the integrand? Well, it's what we've been working with sort of this whole time. Instead of f of pi y of x, I now have g of pi y of x, comma, nu e of x. So I've reintroduced dependence on the normal vector at x. And I've also reintroduced those absolute values that we haven't seen since the very beginning. And really, the way that this is a corollary is you just apply the triangle inequality, you stare at it a bit, and decide when the triangle inequality holds with equality, and it's precisely for convex sets with perimeter P. And so this is an anisotropic analog of Stefan's inequality, recast as a variational problem. Emphasis on the an in an anisotropic, the first an. This hypothesis on G is a little bit unnatural. One can try to attach some physical or geometric meaning to it. But it's seeming that the geometry of your minimizing set, which can sometimes be empty, is really tied into the geometry of this function, this L1 norm of G as a function of its second argument. And so Max and I are still currently looking for a general way of phrasing the solution. Maybe one doesn't exist, but there certainly we can do a little bit better than this. So. Well, having sort of kind of completed the objective of finding some anisotropic analog, I think I'll stop there. Thank you. So that I had been trying to do this for a while, and I'd been thinking of something in the sort of direction that Cornelia had gone, but I never really saw it through, and I think that is sort of what's. Okay, yeah. So work with curves. Yeah, that sounds reasonable. Slicing with. Yeah. So I would like to go there. The thing is, yeah, the orientation cancellation condition is stated doesn't really make a whole lot of sense for higher codimension sets. But yeah, if we're slicing with different objects, then maybe that does give everything that's needed. And if that were the case, then up to considerations of like integrals actually converging, then I'd imagine a lot of it carries over. Maybe not, I'm not sure. But yeah, great question, thanks.
Thank you, Anna, and well, thanks to the organizers, Max, Mariana, and especially Anna for being here and for bringing us to this not so terrible city of Tampa. Okay, I want to talk about some work I did with my former advisor. Well, I guess an advisor is never former, so with my advisor, Evgenia Malinikova, about some gradient inequalities for Laplace eigenfunctions. It might be a little technical, hopefully not too much, but feel free to stop me and ask questions at any point. I don't have an ambition to actually go through everything that I want to say. Okay, so first I'd like to tell you what Laplace eigenfunctions are, and I'm taking a compact Riemannian manifold M with the metric G, the Riemannian metric G, and the equation for the eigenfunctions is Laplace G phi lambda plus lambda phi lambda equals 0, so lambda is called an eigenvalue, and phi lambda is an eigenfunction. Okay, the Laplace-Beltrami operator is a nice elliptic operator in a manifold when you write it in local coordinates. There's a well-developed spectral theory for this problem, and it tells you that the eigenvalues are of this form. So you have the first eigenvalue, which is 0, and the eigenfunctions are just constants. And then the second non-zero, the first non-zero eigenvalue, lambda 2, and then there's an increasing sequence of eigenvalues going off to infinity. Okay. If the eigenvalues are different, then the eigenfunctions are orthogonal in the L2 sense on the manifold. Let's start with some examples. This is a very general fact. Now we'll go to the very particular. So probably the easiest example of a manifold you can think of is a unit circle, in which case the eigenvalues are integer squared, and the eigenfunctions are you can imagine, sine or square root of these integers, square root of lambda x, cosine or square root of lambda x, and you can sum them together with some coefficients. Okay, so these are trigonometric polynomials, as simple as it gets. Going to higher dimension in one direction, so on the flat torus of dimension d, eigenfunctions are also trigonometric polynomials. So the eigenvalues is those numbers that can be written as sum of squares. There's a ton of those. Maybe in 2D there's not that many, but in higher dimension there's certainly a ton of those. And then eigenfunctions are linear combinations of complex exponentials with coefficients with this, let's try this, yeah, conjugate relation, because we want real valued eigenfunctions. Okay. Another way in which you can go up from the one circle is to consider the sphere instead. And here, so with the round metric on the sphere, the eigenvalues are essentially integer squared. Not really. It's an integer n times n plus d minus 1, where d is the dimension. The eigenfunctions, what are the eigenfunctions there? You take a homogeneous harmonic polynomial on Rd plus 1, and you restrict it to the sphere. And this gives you an eigenfunction with this eigenvalue. Okay? I'm particularly interested in the case when this lambda here is very large, so in sort of in asymptotic properties. And when you get to asymptotic properties, this lambda here is essentially n squared. Okay, it's essentially an integer squared. So in all these examples, what we see is that the eigenfunctions are essentially polynomials of degree square root of the eigenvalue. Okay, in all three, and polynomials in a different sense. These are very simple examples, but somehow they actually capture a surprising range of behavior of eigenfunctions. Particularly, the first case, eigenfunctions are flat in the sense that the L infinity norm and the L2 norm are the same. On the sphere, instead, you have like extreme peaking of the eigenfunction. You can construct eigenfunctions, spherical harmonics, for which the L infinity norm is a lot larger than the L2 norm. Okay, so there's actually quite a range of behavior, but we see that there is like a polynomial structure to this. So the sort of the far-reaching idea, motivating principle behind all of these is that an eigenfunction phi lambda in general looks like a polynomial of degree approximately square root of lambda. Okay, this is both exciting and scary because polynomials are hard. Okay, you can do a lot of things with polynomials. That means that you can't limit yourself too much. So I'm going to give you some evidence to this claim, and I have to start with one of the most influential results in the field, which goes back to Donnelly and Pfefferman in 1988. They wrote a series of influential papers where they proved a bunch of things about eigenfunction, and essentially in the last 30 plus years, most of the results in the field are trying to do better than Donnelly and Pfefferman, moving from there and trying to. So they really kickstarted a lot of the techniques in this field. So they proved this growth estimate, for which I clearly have a typo. So this estimate is certainly true but vacuous. But they proved that if you take a ball of radius 2r and you estimate the supremum of your eigenfunction, then it's controlled by exponential constant square root of lambda times the supremum over the ball of radius r, clearly. This is a doubling type inequality. Okay, so there's no 2r on the right-hand side. So this inequality is true. As I said, it's a doubling inequality. It tells you essentially, it gives you a bound on the growth of eigenfunctions on concentric balls. A sort of an immediate consequence of these, if you go down the scales, is that the vanishing order of an eigenfunction at any point in the manifold is bounded by constant times square root of the eigenvalue. Okay, an eigenfunction cannot vanish to arbitrary order. Okay, very good. Yeah, again, if I'm not making sense, stop me at any point. Another way more recent result that I want to mention, because I consider it really one of the crown jewels of the theory of unique continuation, it's a result by Sasha Logunov and Evgenia Malinikova in 2018, let's say. It tells you this. So you have B, which is, say, a ball or an open set in the manifold, and E, which is a subset of this ball with positive measure. Can be arbitrarily wild. I require no structure on E. Then you can estimate the supremum over the ball of the eigenfunction phi lambda by a constant times the ratio of the measure of B and E to the power constant square root of lambda times the supremum over this arbitrarily wild set E. Okay, this is really comes from polynomial inequality. The version for polynomials where here you have the degree is called the Rimé's inequality. It's a classical polynomial inequality. I think it was proved at the beginning of the 20th century, end of the 19th century. Okay, and the proof there for polynomials is very explicit. You compute the extremizers, which, no surprises, are Chebyshev polynomials as usual in this polynomial stuff. The proof of Sasha and Eugenia is very different, of course. But yeah, I think this is a sort of striking inequality. It tells you that, in this sense at least, eigenfunctions really do behave like polynomials. Okay. Now I'm going to explore, I'm going to go to polynomials actually and explore a couple of actual inequalities for polynomials. Very classical inequalities, which are called usually Bernstein or Bernstein-Markov inequality. This is usually called the Bernstein inequality. And for a trigonometric polynomial Tn of degree n, you can bound the supremum over the whole circle, say, or the interval minus pi of the derivative of the polynomial by the degree times the supremum of the polynomial itself. Okay, and then this is the first inequality. The other inequality is usually called the Markov inequality. Instead, if you take an algebraic polynomial of degree n, then you can bound the supremum of the derivative on an interval, say the interval minus 1, 1, by n squared, by the degree squared, times the supremum of the polynomial. Okay. Eugenia would say these inequalities that we all learned in high school. I certainly don't know any of this in high school. I don't think I knew what a polynomial was, so, but yeah, I believe Eugenia did. Okay. More seriously, what I want you to note is that this, the Bernstein inequality, first one, is a global inequality, right? You're bounding the trigonometric polynomial on the whole circle. Okay. Well, this Markov inequality with the degree squared is local. Okay. And the other thing I want you to note is that you really need this n squared, this degree squared in the Markov inequality. Okay. Again, Chebyshev polynomials are extremizers, and they attain the equality with n squared. This is a stupid drawing of a Chebyshev polynomial. You can see that the problem is that the zeros of the Chebyshev polynomial gets tighter together towards the extremes of the interval, and that's why you need this degree squared. Okay. Okay. Back to eigenfunctions. So, sort of an immediate analog of inequality 1 for eigenfunction is true and is pretty easy. So this is a global inequality. You can bound the supremum over the whole manifold of the gradient of your eigenfunctions by the degree of this polynomial, which is constant square root of lambda, times the supremum of the eigenfunction over the whole manifold. I'm not attributing this to anyone because this is sort of an easier result. It's an elliptic estimate. You can prove it pretty easily. Just a quick shout out. This is actually true even if you take linear combination of eigenfunction. This is a result that I like to mention every time I give this talk because this comes from the these guys come from the theoretical machine learning sort of data analysis community. But this is a math paper, and this is an impressive result that I think it's not well known enough in the community. Anyway, this is for global inequality. I'm more interested in sort of the Markov style inequalities, so local inequalities for eigenfunctions. And again, you ask yourself a question about eigenfunctions. You first check Donnelly-Pfefferman, okay? Because probably they've done something, and they did. Okay, and in another paper, they have this sort of local type gradient inequality that tells you that the supremum of the gradient on a geodesic ball is bounded by lambda to some dimensional power over r times the supremum of the eigenfunction. The 1 over r is a natural scaling. You just, you rescale your eigenfunction, you see that this needs to be there. The dimensional power is just what they get. They prove an L2 estimate first, and then they do a sort of a relatively cheap thing to go from L2 to L infinity, and then they pick up this dimensional power. They conjecture that you should have the inequality with square root of lambda instead of a dimensional power, which certainly would be sharp. Okay, and so sharp that in fact it's the first time you look at it, you think that it's maybe too good to be true. And that's what Eugenia told me several years ago at this point. She's like, find a counterexample to this, and then I spent a bunch of time and I couldn't find it. So I'll tell you why this is actually reasonable. It got me a while to get to the point to believe that this is a reasonable conjecture. Because this is saying, I put a reminder, remember the n squared in Markov. It's more a reminder to myself. Because this is the degree of the polynomial, right? And this is a local inequality. So this inequality, if true, would tell you that eigenfunctions are better than general polynomials, right? Because you don't have the degree squared in here. You just have the degree. So this conjectural inequality is extremely strong, okay? some evidence towards this direction. It's a sort of a forgotten. Yes, Dominique.
Sorry, can we go back to the previous?
Sure.
Did I miss something as to why we might suspect the D to be removable with projection?
No. I guess it's for polynomials you don't have a dimensional exponent. Okay. I think the hard part is whether you have here square root of lambda or lambda probably, but the dimensional exponent does not appear in polynomials. If you believe polynomial eigenfunctions behave like polynomials, there shouldn't be a dimensional exponent. Okay. So further evidence is there's a sort of a forgotten paper of Szego from the 1940s where in dimension 2 and 3 it proves that if you have a harmonic polynomial, so not just a general polynomial, but a harmonic polynomial in RD, then you have this local Markov inequalities with the degree of the polynomial, not the degree squared. Okay? And the general dimension, you can find the proof in this was, sort of rediscovered every 10 years or something by someone. Sort of the most recent and complete reference is a paper by Jordi Marzo in 2007. Okay? And Szego actually computes the exormizers, which in this case are clearly not the Chebyshev polynomials for once, because they are harmonic. And they're exotic exormizers. It's an interesting paper. Further evidence, it's something that's calling a theorem. It's maybe too much. It's a proposition that I shamelessly attribute to Eugenia and I. It probably was known by someone else at some point. It's just not written. So if you have a harmonic function, so I'm talking really about a Euclidean harmonic function with bounded frequency, probably all of you or most of you know here what the frequency is, but I'm going to tell you in a second. It's a measure of growth of a harmonic function. So if you can bound the growth of your harmonic function in a ball of radius big R, then you take any ball of radius little r, which is less than r over 2, and you can have a sharp Markov inequality for Euclidean harmonic function up to that scale. Okay. We proved this by really just like expanding into spherical harmonics, and the approximation is good enough to allow us to conclude. Okay. Our main result is something that is more general than this, even though it's less precise, and it's not going to look more general, but I will tell you why in a while. So this is the result. So back to compound Riemannian manifold. We want the manifold to be smooth, and doesn't need to be C infinity, but it cannot be C1 or even C2. We need some degree of smoothness, and I'll tell you later why. So the result is you take any epsilon, then there is a constant, so you can bound the supremum of the gradient of an eigenfunction of ball BR by this constant at the maximum of these two quantities, square root of lambda times log lambda to 2 plus epsilon over R, and lambda log lambda 2 plus epsilon. You can ignore the epsilon if you want. You can say that epsilon is equal to 1, and then this constant will not depend on epsilon, just on the manifold, and then you get log lambda to the third. If you ignore the lambdas, what is this telling you? That we have the sharp Markov inequality up to scale 1 over square root of lambda. Notice these two terms in the maximum, they coincide when R is equal to 1 over square root of lambda. So we actually proved just the left-hand side. So we proved the inequality at small scales, and then to go to a large scale, we do a trivial thing. Okay? And if you ignore the logs, which I would like to do, but I can't. But anyway, they're there. This is sharp at small scales, and it really looks like this like local Burson inequality for harmonic polynomials. And then here it looks like the Markov with the degree squared at larger scale, so in a unit ball or something. Okay? We actually prove an equivalent estimate, which is you take your eigenfunction, the supremum eigenfunction in a ball, and you just enlarge the ball a little bit with this eta, which is 1 over square root of eigen. It's essentially 1 over this term here. And then you estimate with an absolute constant that depends only on the manifold and not on lambda, the supremum on the slightly larger ball by the supremum on the smaller ball. Okay? This is kind of like the Donnelly-Pfefferman growth estimate, but much finer. Okay? I'm not doubling the ball. I'm really enlarging the ball a tiny bit and then trying to capture the rate at which the constant stays a constant, right? It doesn't, this implied constant here in this swirly symbol does not depend on lambda. That's the whole point. Okay? How am I doing on time? Pretty bad, as expected. Okay, let me just tell you, we actually don't want to think about eigenfunctions, but we want to think about solutions with elliptic PDEs. In this sense, the inequality we have is more general. And what is the connection? If you take your eigenfunction and you multiply it by e to the square root of lambda t, so you add an extra variable, this function is harmonic in the product manifold, m times r. Okay, and by harmonic, I mean harmonic with respect to the Laplacian on M. So it's a solution of an elliptic PD in the versions 4 in local coordinates. Moreover, by this bound of Donnelly-Pfefferman, which this time I wrote correctly without a typo, it has this bound on the growth. Okay, so it's not just a harmonic function; it's a harmonic function with a bounded growth. And if you prove an inequality for these harmonic functions with bounded growth, then you get an inequality for your eigenfunctions at small scales. Okay, so this is to say that the takeaway from this is that I really want to study solutions of elliptic PDEs with a bounded measure of growth. This one is a fine measure of growth. You take the log of the sup over twice the ball over the sup of the ball. Probably a nicer one is what is called the Almgren frequency function, which a bunch of you are familiar with. And let me probably skip it because I have very little time. It's a nice measure of growth of a function that was introduced by Algorand to study multivariate harmonic function. And then in this form that I write here, it was actually studied by Garofalo and Lin. The nice thing about this function is that it's almost monotonic, so it allows you to do nice things. But the point is, what I want here is that this is really the analog of the degree of a polynomial. You can think of a local degree of a solution to an elliptic PD. Okay, and the theorem that we actually prove is for these is for elliptic PDEs with bounded growth in this sense. You don't need to read the result very precisely. It's essentially the same as for eigenfunctions. Just note that here we have n, which again is the degree. It's not the degree squared, right? So we can bound the gradient. So we're saying that solutions to elliptic PDE at small scales behave like polynomials up to log. Okay. I'm not actually sure if the log is. I'm not convinced that the log is just technical. I think it might actually be there. I can't prove it, but I think it might actually be there. Again, this is what we actually proved is an L infinity estimate for a little and large ball. Okay, let's see. Let me try to wrap it up. Maybe a comment on this. If you sort of by almost monotonicity of this frequency function, you can get that the supremum over a ball of radius R2 is controlled by a constant times the ratio of the radii to the power constant n times the supremum over the smaller ball. But this constant c is not 1, right? If this constant c is 1, and you can't get it to, if you follow the proofs for almost monotonicity, you can't get it to 1 in an obvious way. If the constant c there was 1, then this result would be easy, because R2 over R1, it's certainly smaller than 1 plus 1 over n. If you take 1 plus 1 over n and you elevate it to the n, this is a constant, right? Even if n is super large. But you can't take c to be 1. So that's where we have to do some work. By sketch of the proof, I mean that I will not actually give you a sketch, meaning like a children drawing. Okay, it's not an actual idea of the proof even. I just want to show you some drawing. What we do is we take we have our matrix A and we approximate it with the Taylor polynomial of order k. So the first thing we tried to do was to actually, as you would do when you were trying to prove shadow estimates, I don't know, 6 years ago, you try to freeze the coefficients. And then use the result that I showed you before that we had for harmonic functions. This doesn't work. And the reason why it doesn't work, it's technical, but it's a little subtle. And in fact, we put a wrong version on the archive where we had tried to do this. And then we realized that we made a mistake. Okay, so instead of freezing the coefficients, we essentially, we approximate the coefficients with the Taylor polynomial of order k, not just with the first term, right? And we approximate our solution u with the solution of this nicer elliptic PDE with polynomial coefficients on this little ball, and then we can control the difference in this way. Let's see, let me wrap it up. Okay, and then we can use complex analysis because we have a solution of an elliptic PDE with polynomial coefficients, in particular with real analytic coefficients, and complex analysis bails us out. We have this nice little lemma, which is a very sharp version of a three-ball inequality. It tells us that if we have sort of an a priori control which depends on n on this larger ball, and then we control, say, by 1 our analytic function solution of an elliptic PDE with analytic coefficients on the smallest ball, then we can control by a constant in the middle ball. Okay. This is a three-ball inequality, but it's not an obvious one. You need to work for it because I need this constant to be independent of n. Okay, and I need to go to this smaller scale. You can ignore this. So the problem, really, yeah, okay. Let me just mention it. What we do is we actually there's this theory that tells you that if you have a solution of analytic PD with analytic coefficients, you can actually extend it to a holomorphic function in CD. Okay. And this problem behaves pretty well with slicing, and we can actually estimate the holomorphic function in C. And the problem is we have a holomorphic function which is bounded by some power of n in this whole domain. In this domain, these extension domains for holomorphic functions are relatively nice in the sense that here you have these definite angles. You don't get a cusp here. So suppose that this is your baseball. I drew it in one dimension. So this is a ball in RD, and then you can extend it in this way in CD. Okay, and then you want to bound. You suppose you have your function that is bounded here by 1, and you want to bound it by a constant that does not depend on n at this closest point. This is really, in this case, is an estimate for harmonic measure of this kind of domain with these two angles. It's easy because these angles are really angles, and we can do it explicitly. We can produce an explicit function, that a barrier essentially that gives us the bounds. Okay, I should finish. There's a sharper result in dimension 2, but you have to. I will leave you without that. So thank you very much for your attention, and please join me in thanking again the organizers, and Anna especially.